Oh, oh, yes. Okay, we got the recording going. Good. Yes. So I'm happy to have Tom Gowan from Spire with us today. Here's a plan. I'm going to give a quick overview of the Earthmover Data Marketplace, which is where you can find this amazing data set from Spire, and then hand it over to Tom for the bulk of the time, and he's going to tell you all about the science behind their S2S forecast and how it can be used in a range of different applications. So let's kick it off. This webinar is hosted by Earthmover. We're a mission-driven startup on a mission to empower people to use scientific data to solve humanity's greatest challenges. We come out of the open source scientific Python community, Pangeo, Xar, Xarray, and with Earthmover, we're working to build the scientific data platform of the future that can empower teams of all sizes to work with complex Earth system data sets at scale. Now, why did we create a marketplace and what are we trying to do to change how the world interacts with data? Well, we see three big trends that are all converging that are changing the requirements for how organizations share and access data. A big one, of course, is AI and ML. It's impossible to ignore. The point here is that AI has a voracious appetite for data. AI models, machine learning methodologies are capable of consuming vast amounts of data. And generally, a lot of teams are looking for access to an entire archive. And so in weather, that means the entire history of forecasts, full globe, all ensemble members. There's just a huge appetite for data, and there are models that can make use of that. Another important trend is cloud computing, which makes it really easy for organizations of all sizes to store, manage, and compute on large volumes of data. And in the cloud, we really like to use cloud object storage as the most efficient way to access and store data. But that changes the requirements for data distribution quite a bit. A third trend is open science, the trend of sharing research outputs and data sets openly as part of the scientific process. And this is also a trend that we're trying to support here at Earthmover with the data marketplace. Now, the problem as we see it is that traditionally there's been a big sharp divide between the data provider and the data user. So the data provider, a big government agency with a big data center, data user, a researcher on the other end of that who's going to download some files from the provider. And this paradigm is really struggling to keep up in this new AI and cloud-based world that we're living in. For weather, typically forecasts are handed out as just a big stack of GRIB or NetCDF files, and those give pretty poor performance out of the box in AI workflows. And so we're seeing data consumers that are ingesting that data, transforming it to all kinds of different formats to make it more useful for analytics. And that has a high cost for the data consumer in terms of latency, in terms of overhead, in terms of engineering complexity. Now, fortunately, there's a new standard emerging. This is the standard of analysis-ready cloud-optimized data, a concept we've been working on shaping for many years, and now really seems to be taking off. And the idea is that analysis-ready means that data are organized into these hypercubes that allow arbitrary slicing across all of the data set dimensions without having to think about, the details of files and how data is organized into thousands of files. And cloud optimized means that those data are stored in cloud object storage using a cloud native file format that makes them easy to read and integrate into workflows. So at Earthmover, we're building a whole platform around this concept of analysis-ready cloud-optimized data that includes data governance through our RayLake platform, data analysis and visualization through our Flux API layer, and then the most recent addition is this concept of the data marketplace. So before we launched the marketplace, our platform was useful for orgs to manage their own data within their own teams, but very much within silos within each organization. And with the marketplace, we're enabling exchange of data, secure and performant exchange of data between organizations, where in acquiring a new data set is as easy as flipping a button, and there's no big complicated ingestion process required. So we're thrilled to be working with a bunch of amazing data providers within the marketplace. And today we're going to hear from one of the newer ones, Spire, and Tom's going to tell you all about their data set. Before I get there, I just want to summarize, wrapping up the benefits of this approach that we see for both data users and data providers. When you access data this way, you get instant access to these high quality analysis ready data sets, and you can bypass the whole data ingestion transformation part. We have a wide range of different data sets and offer a single access point to both free and open data, as well as commercially licensed data like the data set Tom's going to tell you about. And then on the data provider side, we're trying to make it easier for data providers to distribute analysis-ready cloud-optimized data without having to build and maintain a bunch of infrastructure. If they're already working with Czar and IceChunk, then that is really a no-brainer. And we're giving those data providers a lot of control over how their data are stored, how they're licensed, and providing metrics to quantify usage, impact, and impact. Okay, so with that, I'm going to turn it over to Tom. Tom is going to tell you all about this new forecast data set that Spire has created that you can get through the Earthmover data marketplace. So Tom, take it away.
Awesome. Thanks, Ryan. Are my slides showing up nice and full screen on your end?
Oh yeah, looks good.
Okay, awesome. Just so everyone knows, I can't see anything else besides the slides right now, but I think we're going to save Q&A for the end anyways. So thanks, Ryan. My name's Tom Gowan. I'm the Director of Weather Prediction and AI at Spire Global. So I lead all of our teams involved in the research and development of both our physical and AI models and the deployment of those models into operation. Today, I'm going to give an overview of Spire as a company, quickly dive into our forecast products, and then really dive a lot deeper into our S2S model. And then we'll do a little quick view of a sample notebook, looking at the data on Earthmover and showing some analysis. And then we'll end with Q&A at the end. So Spire is what we call a space-to-cloud data and analytics company. We build, design, operate the world's largest multi-purpose constellation. So we design, build all the satellites we have in space. We then typically launch them on SpaceX or whatever rideshare option is available. All of our satellites are RF or radio frequency detecting satellites. So we don't do imaging, we don't do communications. It's all just listening for various radio frequencies. I'll be diving into the weather side, but I just want to note that we have an aviation business unit where we basically listen for all ADS-B messages coming from planes so we can track planes globally. And then we have another business unit called Space Reconnaissance. And this is sort of looking for signals of opportunity. So we do one thing called RFGL, which is radio frequency geolocation. We can essentially tune the antennas on our satellites to listen to any kind of signal. Think GPS jammers in war zones, dark ships lying about their location, things like that. So that's kind of more on the military application side of things. We've been around about 15 years. We started in Silicon Valley as a very small startup, went through various rounds of funding, raising, I think, a couple $100 million. Then we went public on the New York Stock Exchange about 5 years ago. To date, we've launched over 240 satellites. They're small sats or nanosats ranging in size from 3U, which we call like a shoebox or wine box size, up to 16U. And then we're going to get a little larger than that in the future. 16U is roughly mini fridge size. So I've launched 240 of these. Typically these days, there's a SpaceX rideshare launch every 2 to 3 months. We typically have a handful of satellites on those. And we have roughly 80 or so in orbit. They're only designed to last about 3 to 5 years. We also build and operate many ground stations around the world so that we own the entire value chain from building of the satellites, the data off them, the processing, and then the delivery of products and data to our customers. I think we're up to about 400 employees or so over North America and Europe. I'm out of our main weather and engineering office out of Boulder, Colorado. We have an office in DC, Toronto area of Canada, and then we have offices in Glasgow in the UK. That's where most of our satellites are designed to manufacture. Luxembourg and Munich. There's a couple other small ones I might be missing, but those are the major ones. All right, so now we're going to jump into the weather side. So there's really 3 key data sets that we get from our constellation that we use within our weather models. The one we're most known for, the one we've been doing the longest, is what's called GNSS radio occultation, where GNSS stands for Global Navigation Satellite System. So we essentially listen for signals that come from GNSS, such as GPS, and we capture those signals that go from space through the Earth's atmosphere and back into space. When they go through space, there's a bend and a time delay that occurs. So it's a direct function of temperature, pressure, water vapor. And we can also back out to electric content in the upper atmosphere. This is a very proven technique over decades. It's extremely accurate, unbiased measurements, similar to that of launching a radiosonde as part of a balloon. The big advantage here is that we automate this. We get up to 20,000 of these around the world globally, roughly evenly distributed. So we're capturing areas where balloons are not available, such as over the open ocean waters, sparsely populated regions, and areas like that. And this data is very important because most satellite radiance data needs to be bias corrected in some way. Typically, you use weather balloon data for that. That's not available over a lot of areas, but RO can be used to bias correct all forms of radiance satellite data. So we sell roughly 50% of the RO profiles we get, the raw data, to NOAA and EUMETSAT in large pure data buys. Almost every public model you use, from all the ECNWF models to all the NOAA models, are ingesting Spire RO. Most studies indicate that RO is the number 2 or 3 most important data set that gets assimilated into NWP models. If you search around, there's a lot of research on our data and the impacts it has, especially from ECNWF, UK Met Office, NOAA, and others. We also do what's called GNSS reflectometry. This is similar to RO, but we look for the reflections of these GNSS signals off of land and water. Over land, we can back out the dielectric properties of the land surface, which gives you a rough estimate of soil moisture. And then over the open ocean water, you can get a measurement of the roughness of the surface ocean water, which gives you wind speed if you back out the background swell. We can also get sea ice altimetry from this data as well. The new big arena we're moving into is hyperspectral microwave. So we just launched our first hyperspectral microwave sounder. It's actually the first ever hyperspectral microwave sounder launched into orbit from any entity in the world. So the advantage here is that instead of having tens of bands to measure background microwave radiation from the atmosphere, we have hundreds of channels. And we're also able to, and this covers measurements, very high vertical resolution swaths of temperature, humidity, rain, snow, and ice, especially near the boundary layer. Another advantage is that there's growing RFI threats, and having hyperspectral microwave, we're generally safe from the degradation that may occur with traditional microwave sounders. So this is where we plan to build out. This is kind of our plans for our next big constellation, which nicely couples to the microwave constellation. So we have all this data. We really heavily focus on data assimilation at Spire. This is kind of a brief schematic looking at our overall DA system. In addition to those 3 Spire data sets I mentioned, we also take advantage of all public data available. So we have live feeds of all the NOAA data, and then we use the EUMETCAST system from EUMETSAT. We have a dish installed in our office in Glasgow in the UK. We subscribe to the lowest latency possible live feeds of all publicly available satellite data. All of this data we assimilate to a background ECNWF analysis. They generally, the community has agreed, they produce the best analyses. So we take that the instant it's available and assimilate all this other data on top. We then run our in-house cloud ingestion and analysis system. This is essentially a system we built out that takes all types of radar, satellite, and other observations to create 3D representation of clouds and precipitation. We then bring that into the model in sort of a hybrid data assimilation technique. And then we produce global DA analyses and then regional analyses for our high resolution regional models. So these DA analyses power our forecast portfolio. I'm going to briefly go over this and then dive much deeper into the S2S model. So on the short range side, we run a physics-based model. We call it just our high resolution forecast system. It's at 3 kilometers. We cover the entire continental United States, all of Europe and Southeast Asia. What's fairly unique is that we go all the way out to 6 and 7 days with these forecasts. So if you kind of want to understand the actual impacts and the detail of resolving convection beyond that 3-day period, that's a unique position that our forecast can fulfill. At high accuracy, we have verified against ECNWF and HER and others, and show that we are able to often outperform them with our use of our own DA system that uses ECNWF background data on top of our data assimilation. On the medium range, we currently run a system we call AIWX. This uses our global DA system tied to an open source AI model. There's a lot of work. We're really focusing on this area right now. I'm going to be touching on some updates that are coming to the weather scale very soon. But this is a 1/4 degree resolution. We run it 4 times per day, up to 20 days with 30 ensemble members. And then we have our S2S subseasonal model, which I'll be really diving in here. This is a completely in-house trained, designed, built model at 1/2 degree resolution, run once per day, up to 45 days with 200 ensemble members. We also have a point optimized system, which basically takes all the forecast data from these products, as well as many publicly available sources. And then we train that data to get optimized point forecasts anywhere in the world that there's high quality station data. So now diving into our subseasonal forecast system, this is the data set we have hosted on Earthmover. So like I said, our kind of thought process here was there's a lot of competitors in the weather space, but there's not as many options that have taken AI and proven the benefits of it in the subseasonal space. And our thought process is if trained properly and designed properly, AI could find linkages that would ultimately improve subseasonal forecast systems that aren't necessarily encoded in our physical models today. So our model at a high level is similar to the traditional kind of weather AI weather models that are out there. It uses Aero5, it uses ECNWF with our DA on top. But what's unique is that we actually pre-process the data into daily mean statistics before the training period and at inference time. So we take those 40 years of Aero5, not only atmosphere data, but also ocean and land data as well, because that obviously matters when you get beyond weeks 3 on the kind of the subseasonal timescale. Process that into daily statistics. We then have an in-house model we've designed. It's an autoencoder with the CRPS loss function, which has generally become the gold standard for any probabilistic model. We then fine-tune on multiple years of our initial condition data. This is that daily post-process statistics based on ECNWF plus our DA system. And then we generate the 200-member ensemble up to 46 days once per day. So we make the raw data completely available. It's obviously quite a large data set, but we also have put a lot of effort into creating products that are more usable for ag, energy traders, insurance, et cetera. So down here, you're seeing a couple of these specific products we developed off our data set. We develop weather regime charts, so likelihood of various weather regimes, following a lot of the research on this, generally led by Simon Lee and others at University of Oklahoma. We've worked with a couple of key customers on this to really nail down what traders generally look for over North America and Europe. We do weather anomalies, we do percentiles and extremes, all based off 30 years of Aero5 climatology. So verification, we've been working on this model for a little less than a year now, and we just had a major update, which really was a step change in the overall skill of the model. Obviously, our key benchmark is the ECNWF 46-day forecast, or the ECNWF S2S model. This is kind of the gold standard. This moves markets the most in that subseasonal timescale. Here we're looking at CRPS, so continuously ranked probability score, a very commonly used metric for evaluating probabilistic forecasts. This is verified globally over a 45-day period. We are using 45 days because we have fine-tuned the model up to the end of 2025. So we don't want any of that fine-tuning impacts to bleed into the forecast. So it's currently validated every day from January 1st to February 15th. We are going to be expanding this to a full 3-month verification period now that we can verify that full 3 months. But nonetheless, at a global scale, we find that this is plenty of data to get a strong signal. And this is during the winter time, which is an important time to get subseasonal forecasts correct. So in these plots, lower is better for CRPS. You want a lower score. We're seeing temperature on the left and then 500 millibar heights on the right, or 500 millibar geopotential. The gray dotted line is climatology. So that's if you made a forecast purely based off just using climate. ECNWF is shown in that sort of bluish teal color, and then the S2S forecast that is, and then Spire is shown in red. You can see that looking at temperature, we are able to outperform both climatology, showing that we have skill all the way out to 6 weeks, as well as the ECNWF. And then 500 millibar heights. This is generally among all the research I've seen a much harder spot to beat the ECNWF physical models, especially in the subseasonal lead times. But you can see beyond weeks 3, we do show an edge there over the ECNWF, and then we maintain skill going all the way out to week 6, as shown by beating climatology. So a brief look at what's coming next for future updates. So we're very happy with the current status of the model, but we want to keep to improve it. This is a big area of research and development here at Spire. We're going to be adding a lot more variables related to soil moisture and soil temperature, which are key drivers on the subseasonal timeframe. So we're going to be adding more layers of soil moisture and temperature. Right now, we just have the top layer. We're going to also be adding and testing the impacts of snow depth and sea ice. We also want to incorporate more Spire data. So completely separately, we build a Spire soil moisture analysis based off that GNSSR data that we have. We have a 40-year history of that as well. So we plan on training the model on that and then using it at inference time. We're also going to be investigating coupled model. So basically a couple separate AI models for the atmosphere, ocean, and land. And then we're really pleased with the results of this model. So we're going to be taking everything we've learned about building a subseasonal model, and we're now going to apply it to the weather scale. We're going to use the same sort of architecture, but tailored to the medium range, so higher resolution. A huge value add, we believe, is running these AI weather models at higher latency than every 6 hours, which how most of them are run. So this is going to be trained from scratch to be a rapid update model, and then work with our upcoming AI DA system. So more to come on that soon. So on Earthmover, you'll see that we've, for the last month or so, we've had Spire S2S forecasts available. The variables we have are surface, 1,000 millibars, 850, 500, 200. Standard suite of variables, so temperature, wind, precipitation, pressure, radiation, geopotential height, humidity. And then we have these products I've kind of touched on, and these are known as groups on the Earthmover platform. So we have the mean and standard deviation, percentiles, climatological probabilities, and anomalies. For chunking, each variable is chunked such in the array shape of 1, 1, 361, 720, where reference time is the initialization, step is how far out in a certain forecast, and then lat and lon. So yeah, right now we show the 15 most recent issuances. It is behind a paywall for those forecast products. And then the new inits are replaced by the oldest. You do want to make sure if you're looking at this, you do sort by reference time because they're not necessarily chronological. Something I want to make really clear, I know we have not had Hindcast to date, but that is coming next week. There will be a 3-month and growing Hindcast data set available, completely open and free for anyone to download, test, independently verify before approaching us for access to the live forecast feed. So very excited about that. I think that'll really encourage people to test our data. All right, I'm going to quickly switch to a notebook just to show a sample of reading in this data and processing it on Earthmover. And then we'll jump to Q&A after that. All right, Brian, is that sharing on your side, the notebook?
Looks good, but you may want to zoom in a little bit, just like increase the font size uh, if you want people to see what's on here a little better.
Oh, there it
Yeah,
goes. Big
there you go.
lag in
Yeah,
increasing the Chrome font size.
yeah, yeah.
Let me give that a second and make sure it blows it up a little. Okay,
Looks great.
cool. All right, so we put together a quick notebook to kind of show what it looks like, an example of reading it, looking at the data on Earthmover and doing some kind of analysis that an energy trader or someone looking at the overall weather pattern would be interested in. The goal here is not to show off the details of the code. It's really just to show an example. We will find a way to make this notebook publicly available so others can use it. We do plan to actually write a blog post on Earthmover. Myself and my colleague Max Grover will be working on that. So that'll incorporate this notebook, and we'll probably figure out a way to link it in there. Okay, sorry for the lag, but what I'm going to quickly show is opening up the data set, showing off how it's structured. We'll look at a 500 millibar plot for weeks 1 to 6, maximum temperatures, open our weather regime plots. Sorry, it's a little laggy here. And then we'll look at some point forecast of various energy centers across the US. Whoa.
What happened
There's
there?
huge lag here. Yeah, I think I clicked zoomed in and there's a huge lag on the zoom for
Huh.
some strange reason. Let me stop sharing and come back in here.
Yeah, maybe that's best.
Yeah,
I was like, whoa, we don't need to zoom that
that
much.
was, I clicked that about a minute ago and then I decided to zoom in. 1 second, I'm gonna have to reload the page here.
No problem. Yeah, really excited to see. And this is the just the riff while Thomas bringing that up. This is the unique thing about this way of distributing data. Once you get access to this data set, you can just run these notebooks directly against the cloud data. You don't have to ingest it or download it or, move it into your own databases or anything like that. And this is just designed to make it a lot easier to explore and evaluate and eventually, operationalize those data sets.
Okay, I think this should work now. I'm just going to leave
Looks
it to
good.
size. Yeah,
Yeah,
because I don't
it'll
know what
work.
happened there before.
We'll be able to see the figures. Let's not mess with it
Yeah.
anymore.
Yep. Cool. Okay. So just kind of loading in standard Python modules to access it. We do use hvplot for the plots here. Um, like I said, this is one key important thing to note is that this is in 4 different czar groups. So we have a group for mean and standard deviation. That just gives you the ensemble mean and the standard deviation based on all 200 members. We do this for all variables. We then show percentiles. So we pre-process it into 1, 5, 10, 20, 50, 80, 90, 95, 99 across the 200 members. We then do probabilities relative to climatology. So the probability of a tercile event, quintiles, deciles, above a 30-year era 5 climatology. And then we do anomalies also relative to this climatology. And like I said, we chunk the variables in 1, 1, 361, 720, where that's init, forecast out, forecast step, lat, and lon. And then here's just looking at a sample variable. So this is temperature. So we read it in the full temperature variable for a single forecast. You can see 46 outputs. That's 1 output per day. One thing I might not make clear is we actually train this model with a 24-hour time step, which sounds crazy if you're used to doing traditional physics-based modeling. But for AI modeling, this helps with error growth. And when you're looking at subseasonal forecasts, say at day 30 to 45, you don't really need a 6-hourly output forecast because the details don't mean much at those lead times. You're really just looking for signals, generally on the weekly scales, even opposed to daily. So that's a big win we had in actually reducing the overall error growth in the models, doing 24-hour steps within the actual model as we rolled it out. Okay, so now I'm going to just quickly go to a few plots. So a really common variable to look at to understand, the future weather pattern and setup, and then before you relate that to the actual regime, is the actual 500 millibar anomaly chart. So that's what you're looking at here over North America. Each panel is a different week. I believe this is for our latest forecast initialized today. As you can see, there's a bit of a trough moving from the west to the east. We were cold and rainy all week here in Boulder. That's now transitioning east. And then you can see as we go out in time, we generally head to a much more ridgier pattern, especially out west in the middle of the country, which is kind of more typical as we head into summer. Same plot over Europe. Looks like it's quite warm in Europe right now. So it looks like it's going to be a pretty stable ridging pattern for the foreseeable future out there. Now looking at that same plot, but this time looking at temperature anomalies. Obviously, something we see our forecasters looking at, or our customers looking at all the time. As you can see, these roughly correlate to that pattern we saw with the cooler temperatures in the middle of the country and out east. I think Ryan mentioned it's cool and rainy in New York City today. This is obviously a 1-week average. Look at the anomalies, and then beginning to warm up with time. That's similar over Europe. It's quite warm over Western Europe right now, but it looks like that overall ridging pattern will persist as we head out in time. So this is our weather regime product. I want to be clear, this is not currently hosted on Earthmover because we actually give it out to customers as a CSV. So if you want to look at our data, we can set you up with an API through Spire to actually look at these weather regime outputs that we have pre-computed. We spent a lot of time on really nailing this down because we believe most people in the subseasonal community really favor looking at these types of charts as a really ideal way to aggregate and visualize the data that comes out of these models. Essentially, what we do is we perform an EOF analysis and define these what do we do? 5 well-known regimes over North America, and then I think we do 7 over Europe. And then we look at each member and see which regime it's falling into based on that EOF analysis. So what you're seeing over the continental United States is we're right now in a Pacific Ridge pattern. At least that's what our S2S model says. We'll be transitioning into a Pacific trough, most likely. So most members have a Pacific trough appearing in that day 10 to 20 timeframe, and then growing chances of a Pacific Ridge as we go further out in time to that 6-week period. Over Europe, right now have some looks like European blocking occurring, but that's going to quickly transition into Scandinavian trough. And obviously, as you go further out in time, like any S2S model, the model does trend towards climatology. But we do see in our verification that there is a signal. We are better than a raw climatological forecast. So it's obviously harder to weed out the signal you're seeing and further lead times. But we do see it there in our verification. And then just a couple plots showing point data. So this is looking at major sort of energy centers over various energy regions of the US. So we took a bunch of major cities here. What we're looking at here is our temperature forecast as a function of lead time at a point. And then we're looking at the nested bands are probabilities. So the 1 to 99, 5 to 95, 10 to 90, 20 to 80. A nice way to kind of look at the actual spread in the model with forecast lead time for various cities in North America up top, and then for Europe down below that. And then lastly, this is looking at the maximum temperature anomaly aerial averaged over various energy regions of the United States. That's PJM, MESO, ERCOT, and NY ISO. What you're seeing here is most of these regions, because they do fall in the eastern half of the US, are cooler for that first week. So aligning relative to climatology, these are anomalies. Cooler for that first week, then warming up and remaining a bit more warmer than climatology, except for ERCOT, which appears it'll trend a little cooler than climatology as we head out to that week 6 timeframe. So that's all I have for this. Like I said, we will make this available to those who want to use it as a quick way to read in and pull in our data. So that's all for me. Happy to open this up to any questions, or if there's anything you want to add, Ryan, happy to have you speak as well.
Fantastic. Thank you so much, Tom. I learned so much from your presentation. Just as a procedural question, Margaret, how do we want to do the Q&A? Is there any like platform feature? Can the audience raise their hand? Like, how does it actually work?
They can raise their hands, but I actually think the more effective thing is to use the webinar chat, and then we can see the questions.
Cool. Is it possible for the audience to actually come on audio or on camera, or is that not
Sadly, we
allowed by
had
the
too many
system?
people for that.
Okay, cool. Well, while we're getting some questions going from the audience in the chat or through raising your hand, I actually had one that I wanted to ask Tom just as a warm up here. I love learning about the satellite constellation. It's really cool to see all of the different you know, observations. It was also cool to see the extra skill that your S2S model has over ECMWF. Are you able to track like the impact of your proprietary observations down to those like skill metrics and figure out what it actually is that's making the forecast more skillful?
Yeah, we have not dug too deep into that. I'll admit that to date, since the model's relatively young, the emphasis has really been on actually building out a model and architecture that's as accurate as possible. I did mention that we really are mostly using ECNWF data right now because our
Got it.
previous DA system was designed for global NWP models. We're redesigning that right now. So we're basically doing ECNWF initial conditions with Spire RO layered on, but we have not looked at the direct impacts. On the subseasonal scale, obviously the model matters a lot more than the initial
Yeah,
conditions in
got it.
general. Yep.
Cool. Okay, so we had oh, is there a separate Q&A function, Margaret? Someone mentioned a Q&A. Is that oh, there's a Q&A
There is
thing. Okay,
a
I see
Q&A
it.
function, yeah.
Okay, great. I opened that. So we have a question from Srihari. Do you have similar skill across seasons for weather patterns, summer versus winter versus shoulder?
So for this exact model run, like I said, we fine-tuned it up to 2025, so we have not been able to evaluate the whole seasons. But in previous model runs, I can note that we see very similar skill, like the relative skill, no matter which model we're looking at, persists season to season. So I would expect to see this same pattern you see in these 45 days. If you look at the global maps, you can see differences region by region because we're only looking at 45 days. But when you globally average it, we see very persistent skills, and that 45 days is enough to capture the overall skill of the model across all seasons.
Very cool. Okay, there's another one coming from Margaret. Which of the Spire datasets are going to be on the marketplace, and why would I get it there instead of direct? This is an interesting question.
Yeah, so right now, like I said, we have S2S forecasts. Next week, we're adding the S2S hindcasts, so you can evaluate them in these hindcast runs. I do want to note that they are exactly like our forecast runs. So they do not cover any training, any fine-tuning period. They use true initial conditions, not error 5. They are truly forecast data sets. So that will be there. After that, I want to bring over our high resolution forecast. This is a much different forecast, but physical short range forecast. We do plan to bring that over. Why we would bring it over here? Your guys are developing a marketplace that everyone is going to learn, understand. It's really designed for true, large multidimensional geographical data sets as opposed to grid files, which we do use, but most customers aren't comfortable for. And I think there's going to be a lot of eyes on this marketplace. So I want to get our data here as a secondary option for those types of users as you guys build up a customer base here.
And maybe I'll just like editorialize a bit on that. We know our data providers have a lot of different ways to distribute data, and there's different customers who want different things. What we're trying to do with the marketplace is serve that data science user base, right? So there's a lot of weather forecast data consumers who just want a CSV file of their location, and that's great, right? But we're seeing an increasing number of teams that want to consume the data in a more raw form, and build their own models and value on top of that. And so I think that's where our marketplace and our approach, our cloud native approach, really shines. Okay, so there's a couple more questions in the Q&A from Dia. Hi, Tom. How is the skills for the maritime continent, Southeast Asia, for the precipitation pattern?
I'll admit that we have not verified precipitation yet, but the good news is the full 3-month archive is going to be up next week, and you're happy to go verify any variables. This is obviously an issue we always run into with customers, is that everyone wants some of their variable verified, and we could just do a massive verification sweep, but that gets messy real quick. So,
well, just to kind of riff on what we've been talking about, once this hindcast is published, is it feasible for users to do their own analysis and answer those questions for themselves? Just come connect to the data and develop their metric of choice and see how the forecast does. Is that part of why you're putting that
exactly.
hindcast out? Yeah.
That is the number one reason. Every customer has a slightly different use case with our data sets, and we just can't possibly cover all those with verification. Plus, we want to be independent verification. So you can quickly download that whole data set, free, open, no need to contact us beforehand, and then evaluate it against your model of choice, essentially.
Very cool. Okay, and then we have one last question here. Uraj is asking, as understood well, you calculate 3-kilometer CONUS EU Southeast Asia AI NWP model. 3-kilometer global model. Is it close or far in the future?
We have no plans to go 3-kilometer global, unless it could be an AI model. I think that generally on these AI models, they've proven themselves on the medium and long range. I think there's still work on the short range. I think we will get to a point once we have higher resolution reanalyses that we do get to a 3-kilometer AI global model. But for now, our strategy is to focus on actual regions at 3 kilometers for physical modeling. So
Awesome.
It's not on the roadmap doing that kind of model. Yeah.
Maybe as a last question, this is the obvious one, but you guys are what's the best way for people to learn more if folks want to follow up and evaluate these forecasts and consider whether they would like to get a commercial license for your forecast? What does that process look like?
Yeah, great question. So I'll send a quick chat here. You can simply just reach out. I did have a slide on this, but I don't want to do it sharing that again. So I'll just put it. You can reach out to sales@spire.com. That'll put you in contact with the proper salesperson. Ryan, I'm also happy to share a PDF of these slides I shared. You can send that broadly. That email is at the bottom of these slides.
Yeah.
Also, feel free to reach directly out to me on LinkedIn, email, wherever. I'm always happy to answer any questions anyone has.
All the attendees are going to get a copy of the slides, so that's great. Okay, we have a couple more minutes and a few more questions just rolled in. So if you don't mind, let's do them. Prasenjit is asking, tell us more about the model architecture.
I can't dive too deep into all the details because we don't completely open source it, but it's an auto encoder model with the CRPS loss function. Like I said, we do a lot with the training data, how we pre-process it into mean daily statistics rather than just instantaneous data. Um, it's roughly, a lot of the inspiration for this model did come from a published model, I'll add. That's the Fucci S2S model that we believe is quite impressive out there. So that was kind of, we didn't directly use their code. Their code's not open source either, but it inspired this paper. And then we added on things like the CRPS loss function to get better probabilistic forecasts.
Okay, great. And then the last one is from Megan. What does the typical integration time look like for Earthmover Marketplace AI-S test data and or on Spire? And can you speak to data access options via Spire?
Um, so yeah, we have our full live API system at Spire. That's how we typically give customers access to the data at Spire. We also have a visualization system called Cirrus, which I did not go over here because it's not at all related to the Earthmover topic. But you just kind of approach us. We will set you up very quickly. We move very fast with sample data. We could direct you towards Earthmover to get that data now that it's hosted here to do your initial evaluation. And then it's sort of your choice if you want to go through Earthmover with the czar data set or through our API for the actual subscription. Um, yeah, that's typically what it looks like, but we move fast. We will do additional bespoke verification for you if requested as well.
Yeah, and I just add as for these different access options, again, it's just about what's a good fit for that specific team that wants to use the data. If it's a Python shop, they love Xarray, they are comfortable with czar. I think Earthmover Marketplace is a great fit because that's going to slot right into the existing workflow. If the team prefers to consume data through APIs, Spire has those, and I'm sure you guys have a lot of other delivery options as well. So
Yeah,
options are good.
exactly. And as I think about it, the hindcasts are going to be really important because we do not have a great way to share large archive data sets. We typically put it in a customer's AWS bucket, one-off thing, which is not efficient. So I think in the future, we are going to be directing everyone to Earthmover to look at the hindcast data, and then they kind of decide if they want to go through our API or through Earthmover for the live data set.
That sounds great. Yeah, and I mean, I think that's pretty standard for the industry. Just throw a bunch of, a couple thousand grid files over the fence at the customer. And then, okay, now it's the customer's problem to figure out how to integrate those. What is a sophisticated customer going to do? Well, they're probably going to transform it into a Zar data cube anyway, so they can work with it. So can we just skip that
Exactly.
intermediate step? That's kind of where we're trying to go with this. Anyway, I think this is a good place to stop. We've reached our scheduled ending time. I want to thank you so much, Tom. This was a lot of fun. I learned a ton. Thanks to all the attendees, and we will be following up with slides and a link to the recording of today's webinar.
Awesome. Thanks, Ryan. Thanks,
All
Margaret.
right.
Thank you,
See you,
everyone, for
everybody.
joining.